Assignment 3 is released today. I thought I'll go over the problems for assignment 3 uh, because for assignment 3, you are essentially required to look at, I don't know how many problems. You are given 4 or 5 problems. Let's see, 5. In all of them, you're dealing with either a mechanical, electrical, or a CT system, and you're required to uh, come up with an expression for describing the behavior of the system, and all of them will be of the form AX equals Y. Okay. Um, I'll go over some of them as to how you go about solving these. The details you can work out. The first one is a system like this. Okay. You have, let's say, a long rope, okay, elastic rope. Okay. And there are forces acting at different points on the rope. And we want to know what deformation this rope undergoes if you have a system like that. And we model this rope as a set of springs. And let's assume there are many. There are n plus 1 springs. This is spring 1, spring 2, so on and so forth. Each of them is a linear spring. Uh, okay, with a spring constant k. So if I clamp this end and if I apply a force F and I measure the displacement, okay, what is the relationship between force, displacement, and the spring constant for a linear spring? Okay, so we'll assume that we're dealing with linear springs, and with spring constants k1, k2, k3, and kn plus 1, and we are interested in, and at each of these points, there is a force acting, which is F1, F2, Fn, and this is the n plus 1 spring. And we are interested in the corresponding displacements x1, x2, xn. Okay. Now, the question is, we want to know the relationship between the set of forces that are applied and the set of displacements. Now, if we write down the displacements as x1, x2, xn, a vector from Rn, and your f as f1, f2, fn, Rn, we need to find the expression that relates these two. And because we are dealing with a linear system, it will turn out that the relationship will look something like this. Some matrix capital K, X. Your goal is to figure out this matrix. Okay. I'll tell you how you go about doing this, but you can derive the expressions. See, if you start with a simple case like this, whenever you're dealing with stuff like this with multiple things that you have to deal with, it's always better to start with the simplest case and see if you can derive the expression for this, and then slowly convert this into a 3-spring problem, 4-spring problem, and then generalize. Okay. If you have the 2-spring problem, how many forces and displacements would we have for a problem like this? Assuming this n is 2, n is 1 here. There is only one force, F1, and there is only one displacement that we are interested in. This has a spring constant K1, K2. See, whenever you have a spring, right? Let's say it's a massless spring. If the spring is stretching, it's being stretched, the forces on both the ends will be exactly equal. Okay. And that's essentially the fact that we need to use for solving this. Okay. Now, if you have this, if you imagine you have 2 clamps and there are 2 springs, and you apply a force in this direction, what would happen? If you apply a force in this direction towards the right, what will happen to spring 1? This one would stretch, this one would compress. The force F1 that you apply will have to work against the stretch in spring K1 and against the compression in spring K2, right? So if you're pulling this spring and this end is clamped, that means when you say this is clamped, that means this is not moving. That means there must be an equal and opposite force here that's keeping it here, right? So if we just consider this spring, right? And if you're applying a force F1 here, okay, there must be a force that is opposing on the other end because you're pulling the spring. That means there is force that is pulling you back. Means you're applying a force like this. Okay. On the other spring, there's still F1 that's acting at this point. This spring is being compressed. That means the wall is pushing on the spring, right? That means there is a force that's acting in this direction. Okay. If there is a force that's acting in this direction, that means on the other end of the spring, there must be a force that is acting in the opposite direction. Okay. Okay. What we don't know is we don't know these forces. All we know is we're applying a total force of F1. Now, whatever force you apply, right, the springs stretch, but they stay here. That means, I mean, this total system is not undergoing any acceleration. That means sum of all the forces that are acting on this entire system has to be zero, sum of all of it. That means the force that you apply here must be equal and opposite to the total forces that are being experienced by the springs at the two ends, right? So that means whatever force you are experiencing here, let me call it FL for the left side end, and let me call it FR. Means F1 should always be equal to FL plus FR. Okay. Now, as I said before, if you have a spring, the forces that would act at the two ends of the spring would always be the same. If this is FL, that means the force acting on the first spring on this side should be FL as well. Okay. If this is FR, that means the force that's acting here should be FR. And we know the spring constant is K1, K2. So now we have the spring constant, and the forces that are acting at the two ends. What would be the displacement x1 here? The stretching of the spring because of FR, that FL, that would be okay. And the amount of compression that this would undergo would be simply now we know both of these. That means F1 is simply K1 times X1 plus K2 times X1. And that is the expression relating, sorry, not X2, X1. This is the expression that relates the force and the displacement experienced by the spring. See, in fact, this says F1 is K1 plus K2 to X1. This is equivalent to saying the two springs are in series, which they are, right? Whenever you apply a force in this direction or in this direction, you have to always work against both the springs. Okay, and that's exactly what we find. Now, this is for a two spring case. That means in this case, your F matrix is simply F vector is F1, X vector is simply X1, and what is your K matrix? So I can express this in the vector. What is my K matrix? What is it? K1, K2 is it? Does that work? Does the matrix multiplication work? Yeah. See, it's a mapping from Rn to Rn, R1 to R1. That means what is the size of the matrix? This will simply be K1 plus K2. You do the same thing for, it is something similar for the three spring case. I'll not work this out, but you can do it yourself. It's F1, F2, X1, X2, K1, K3. All we know is whatever forces we are applying here, has the sum of all those forces should be equal and opposite to the sum of the two forces here. Let me call this FL, this FR. Okay. So this I know, F1 plus F2 should be equal to, sorry, please, FR. Okay. If FL is the force that's acting at this end of spring, the first spring, the force that must be acting here FL as well. That means I know FL is simply K1 times 1. What about here? See, but here is it. Now, at this point, right, there is another spring here. We don't know what is the force that's exactly acting on this spring. Okay. So now, if you consider this point, right, what are the forces that are acting at this point? There is a force F1 that we've applied. Okay. Okay. What else is acting here? You are applying a force in this direction. That means the spring 1 is pulling you in this direction. There is FL. Now, here is the tricky bit. We don't know what is happening to the spring. The spring could be getting compressed or extended depending on how much force you've applied here and what is the spring constant and what is the spring constant of K3. If this is very stiff and you apply some force here, that means this is not going to compress a lot. So this one will end up compressing depending on whether if K2 is very small than K3. So we don't know. All we know is this. If x2 minus x1 is positive, that means if x2 moves a lot more in this direction than x1, then this will get stretched. If x2 does not move as much as x1, this will get compressed. Okay. That means whatever force that acts on these two ends of the spring depends on K2 and the displacements of relative displacements of x2 and x1. Okay. For now, we'll assume that this spring gets compressed. Okay. Okay. Let's call this force F2 or hat, whatever. Okay, we don't know what that force is. All we know is F1 equals F2, sorry. Okay. What about this end? What are the forces that are acting here? There is F2. Now, let's assume this is getting compressed. That means your FR, there is a compression force here, but this would be pushing you back. This spring would be pushing you back. That means this is FR. If this was getting compressed as well. Now, here, we've assumed the direction for the spring on this end. That means the contribution of that force on this end would be in the opposite direction. If this is like this, the other one, the contribution of F2 cap on the other end of the spring has to be in the opposite direction. Okay. Now, if you write this down, this will be F2 plus F2 cap equals FR. Okay. We know that this has to be true, right? If you add these two, there are F2 caps on either side, they get cancelled. F1 plus F2 will be FL plus FR. That means this analysis is correct so far. Okay. Now, all you have to do is write, we know FL, we know FR. What is F2 cap? F2 cap would simply be K2 into, right? How much this spring compresses or extends. Okay. Now, if you substitute all this, you will get a 2 cross 2 matrix. That's your K matrix. Okay. Now you extend this to the n by n case. Okay. That's how you do this. If you have one more spring, instead of F2 cap, you will have another node for which you'll have to find the force balance. And you'll have to introduce a F3 cap and then derive the whole thing similarly. And then finally, what you'll have to do is, in this case, you'll get two equations relating F1 and F2 in terms of K and X. You simplify and then organize it into a matrix form. Yeah. Okay. The second question. Shall I remove this? Yeah. Yes. It's F1, F2, 2F. Force terms. 2. Yes. Okay. This is 2 cross 2. This is 2 cross 1. This is 2 cross 1, no? See, for the next one, you're dealing with an electrical circuit like this. I won't draw the whole thing with only resistors. And you've got current sources that are inputting currents I1, I2, and I3 from at these three nodes, and assume all of them have resistances R. Okay? And the sum of all these currents is 0. The problem is for you to find out the relationship between the currents and the voltages at these nodes, V1. So you number the nodes as you want, V2, V3, V4, V5, V6. You'll have 9 nodes. The goal is to relate the 3 currents and the 9 voltages. Okay. So you'll have to do something like this. So V will be equal to some huge R matrix, resistance matrix multiplied by I. Okay. And for this, you simply use the, what is it called? Kirchhoff's loop, and then another one is node, right? The node equation, where if you have this node, the sum of all the currents entering or leaving this node is 0. And the currents are simply related to the current here relates these two voltages and the resistance of the path. Similarly, the current here, here, and here. And if you write that, you'll get an expression in terms of the voltages of the nodes. Yeah, that's how you do this. Again, see, if you're stuck and you're not sure how to do, just come and contact us. I will leave. And then the last problem is is a simplified version of the CT. Imagine, you can see the picture there. Imagine we have a simple CT setup. where the green triangle is the X-ray source and the red triangle is your X-ray detector, and the gray region that you see in the middle is the object that you're trying to scan. Um, and what you can do, so you fix the intensity of the X-ray from the source, and you simply rotate the detector and the source, and each time you pass an X-ray, and then and then you're measuring the intensity of the X-ray that is obtained here. Okay, if let's assume the intensity for in whatever units is 1 here, and if you rotate it by, let's say, if you keep the source detector pair at different angles, you get a bunch of measurements. Now the goal is, from these bunch of measurements, can we find out the spatial distribution of uh, the attenuation coefficients of this body uh, that we have here that we are trying to scan. That's the goal of CT. We don't know what the attenuation coefficients of the material inside is. By simply sending X-ray through and measuring on the other end what we get, and by doing this at different angles, we're trying to figure out what is inside. Okay, that's the goal. That's the uh, inverse problem, right? Because from the measurements, you're trying to figure out what the parameters inside are. Okay, like we discussed in the previous module, right? What you're expected to do here is to work on the forward problem. Forward problem is, you know exactly what is inside, but what you need to know, what you need to be able to compute is, if I have my source and detector at these two ends, and I rotate this, and I fix the intensity of the source at different angles, if I know the distribution of the attenuation coefficient inside, what would the detector read? Okay, that's the forward problem. You know what you're starting with. You want to know what the measurement will. Okay, and again, it depends for doing the forward problem. So if you the exact physics of the problem looks something like this. Now, if you have a body, okay, of uniform attenuation coefficient, and you shoot an X-ray with an intensity I naught, what would be the intensity that I would get out here? Out. I'll call it IN. Yes. What is it? I naught. So IN. Sorry. And X. No. What is X? Right. This is X. It depends on the attenuation coefficient and how long the object was, or how long did the X-ray have to travel through the body with this fixed attenuation coefficient to get this. Okay. What if I had the body had mu1 here and mu2 here? What would happen to this? What will be I out in that case? Mu1 plus, is it, into X? Will it be X? Are you sure? The length of the whole thing is X. That means with mu1, it only has to travel X by 2, no? Right. Okay. So that's clear. What if this body had a continuously varying attenuation coefficient as a function of X? This is X. And then you shoot a ray I in inside. What would be I out? No, mu of X into X, is it? Yeah, it'll be no here. If there is a continuous for example, if this was like this, right? Then this is okay. But I mean, maybe before that, what if this was length x1 and this was length x2? How would this change then? Right. So it won't be like this. This will be mu1 x1, mu1 x2. Right. That's clear. But what if you have a situation where mu of x continuously varies? So what you will get out, it won't have a simple expression like this, but it would depend on, you would have to do the line. You would have to do that line integral, right? So what will come out is I in is anyway fixed, integral e power minus mu x dx. So you'll have to integrate along the path of your X-ray. This is mu of x, sorry, not mu x. This will be whatever is the length. If this is of length L, this will be from 0 to L. Okay. Okay. This is if you have a body like this. Now, if you look at the CT problem is something similar. You have a source here, or some angle, a source here, and the detector here. Right? Now, instead of having a unidimensional body, we have a two-dimensional body whose attenuation coefficient is really a function of two spatial variables, x and y. Okay? Now, if you shoot an X-ray from this direction with intensity I in, what you receive here will be I out. What you get here will depend on the integration of e power mu x comma y along the path. So what it really depends on the path integral of your distribution of your attenuation coefficient along the body. Okay, that's what I've written there. Now, actually, this is wrong. It's yes, this is. I'm sorry. Yes, this would be e power minus integral mu of x dx. It's correct. Okay. If it's now here, we don't have to worry that this is a two-dimensional object. If you only consider the object along this line, right, then it's equivalent to this problem. So what really matters is what is the distribution of the attenuation coefficient along this line, right? And then you resort to this integral to get it. But of course, in practice, we cannot compute this integral. We'll have to resort to uh, a, a, a way of computing this using a computer. So the way we would do this, you have the source, you take multiple measurements, and you assume that the body can be approximated by you forego the assumption that it's continuously distributed. You make an assumption that the body can be approximated very well into small pixels like this, where within the pixel we can assume that the attenuation coefficient is constant. Okay, with that assumption, let's say we convert the square region into n by n, n pixels along. That means you have total of n square pixels, and in each of these n square pixels, you assume mu of xi comma yi, where xi yi is the position of the uh, pixel on the ith row and the ith column is constant. Okay, if it's constant, then one thing I can do, all I need to do out for any given angle phi at which I shoot my X-ray in, what all pixels my X-ray would go through, and for all those X-rays, the length of the path that the X-ray takes for each of those pixels. Okay, if the if I know the length, then I know how much attenuation happens in this. How much? Let's say this is L1. How much attenuation would happen to the X-ray here? Well, it will depend on e power minus mu. Let's say this is x yj into L1. because it had to travel a distance of L1 with attenuation, this attenuation coefficient. So you'd have to do that for every pixel that it would cross. The pixels that it does not cross don't get involved in this expression, right? And if you know in, then the I out that you would get depend on L1, the attenuation coefficients of all the pixels that the X-ray crosses. Okay? That means for any phi, any angle phi, the measurement that you would get uh, would have, so this expression that we saw earlier, would have terms like this, right? Now, instead of working directly in terms of the intensities, if you take the logs, let's say this will be I in, I out. If you take the log, right, then you have log of I out, I in. There is a product that gets converted into summation. Log of, let's say this is a natural logarithm, ln. Natural logarithm of e of something is simply the exponent. Then this is simply minus plus mu 2. Now let's assume for simplicity I1 is 1 in some unit that we choose. So this disappears. Means my measurement is simply now a linear function of, after you take the log, is a linear function of my attenuation coefficient of each pixel that I pass through and the distance that I travel in that pixel. Okay. That means for any given, see again, this depends on what angle you choose, right? What mu1s and x1s come here depend on the angle that you choose. That means for any given angle, I have one measurement, let's say y phi, some number, right, will be a linear function of the attenuation coefficients and x1, x2. So it would be, I'll, let me write it like this. For simplicity, I don't want to confuse you. You can write this as some mu multiplied by some x inner inner product with some x vector. Okay. Or in the assignment, I've chosen to express the attenuation coefficient as x. Okay, because the x is usually unknown. In the CT problem, the unknown is the attenuation coefficient. I've chosen to express it as x. So, but don't be confused by that. Okay. I mean, I can choose whatever symbol I want. So instead of this, we can write it as A transpose x, where x are your attenuation coefficients, and A's essentially will depend on the distances travel. Okay. Each phi, you get an equation like this. If you do multiple phi's, let's say you do 10 different angles, 1, 2, y10. This is A1, A10. Now, each of this is a row. That means this is a matrix. You have a common x, and you have, this is how you write the forward equation, right? So what you are supposed to do, so you of course need to derive this. What you're supposed to do is this. So you're given three objects like this. Okay? You need to come up with the forward equations for these three objects. Okay, black means it has an attenuation coefficient of 1, mu is 1. If it's gray, then it's 0.5. Okay? Now the question is, how would you go about expressing this in this form, which is basically Ax equals y. These are your measurements. These are x is the set of attenuation coefficients of your body. A depends on the geometry of your problem. Okay. See, one simple way to do this. Okay. In the first case, what would be the size of x? It's just one. There is only one. The body has uniform attenuation coefficient, so there is only one. Okay. Okay. But let's say you're making measurements at multiple. Let's say at 10 different angles. Okay, it means at the first angle y1, I'll get some output, right? But there is only one attenuation coefficient x. Okay, what goes here essentially depends on what is the angle at which you're shooting the X-ray. The angle at which you're shooting the X-ray will determine the length of this line segment that passes through the body. So that will come here. Now, if you make another measurement at another angle, you'll get the same, something like this. What you'll end up having is a bunch of measurements and a bunch of numbers here, but there is only one unknown. But I can still write it like this. What will be the shape of it if I take 10 measurements? I have 10 measurements. I only have one unknown. So what will be the shape of 10 cross 1? See, this is 10 cross 1 vector. This is 1 cross 1. So this has to be 10 cross 1. We are essentially saying this is the list of or a column vector of lengths or the path length for the X-ray through the body. X is simply, and you simply scale the path length by the attenuation coefficient of the body because it's uniform. It's got only one attenuation coefficient. Okay. So that's clear. What about the second problem where you have this? So this has got some attenuation coefficient. This has got something. So this is 1, 1, half, half. So there we only had one unknown or one x, one value for x. What about here? Okay. See, of course you can divide it however you want, right? Uh, to simplify things, it's easier to keep the how you divide this to be as low as possible. Okay, I've not done the problem. My immediate guess would be to treat the four of these because each of these regions has a fixed attenuation coefficient. I would treat this as x1, x2, x3, x4. Okay. If I do that, then I can treat this as one square region through which my X-ray has to pass. But if you say there are only two unknown coefficients, right, then the geometry of the figure that you have to deal with, which has constant attenuation, it's complicated. Because if you have a ray that goes through this, you have to account for what happens here, and then you have to account for what happens here. It might be complicated, but you can try. Okay. My suggestion would be assume these are four, and then for any given phi, you'll have to figure out these the length uh, that the X-ray has to go through the different segments. All right. So here, if you simply take it as 4, you can also try to, let's say you do 10 measurements, what will be the size of A? 10 cross 4. Okay, all right. 10 cross 4, yes. What about the last one? How would, what would be a good way to split this body so that, yeah, 4 plus 4, how would you divide it? Center? Like this, is it? Yeah, I think that's okay. Can it be simpler? The pixel does not have to be square. It can be rectangular also. This is okay. You can do it. You can do it this way. What if you only do this? 3 cross 3. Each of these has a fixed attenuation coefficient, except these are rectangular now, not square. This is another possibility. I'd suggest work out both of them. Okay, is that clear? No. This is right. Okay. here. The way I've drawn it, this is a square. There is a square inside. The length of this, if this is L, this is L by 2. At least that's the, maybe I should have made that explicit. This is L by 2. I'll change that. You can divide it like this, like somebody else said, you divide it into 4 parts and you get 16 pixels where the attenuation coefficient is fixed. I'm saying maybe you can do just 9. This would be x1. This whole region would be x2, x3, x4, x5, x6, 7, x8, x9. These regions would be rectangular. Yeah. See the okay. I'm assuming that's okay. All right. Okay. Now, uh, before we proceed, right? If you have any phi, how would you figure out what all pixels my line goes through? And how will you figure out what is the length? So, how do I figure out these lengths? This one, I mean this. How do you figure those out? Okay, that's something you'll have to think about. Dimensions are fixed, right? The dimensions don't change. So, for example, let's do a simple case, right? It's like this. The way I've drawn it, right? The X-ray always passes through the center of the body, no matter what angle you choose. So if I choose some angle, it's like this. Now the question is, how do we figure out length and this length? Because that's the length. So here we know the attenuation coefficient is fixed. That means I only have to worry about this length. Then I know the intensity of the X-ray that comes out of here. And then I have to figure out this length. Then I know the intensity of X-ray that comes out. That's the intensity picked up by the detector. How do you figure this out? Okay. You can think about that. That's essentially what you'll have to do. Okay, all right. Okay, that's all I wanted to say for the assignment. Now, the rest 15 minutes, we'll quickly start the next module. Yeah, I hope that's clear. Again, I encourage you to work in groups, but don't please copy the answer. Write it yourself. Okay. We won't do a recap like we usually do because we are short. We'll move on to the next module, which is on orthogonality. Okay, we've talked about some of this before. We've talked about let's say we're talking about vectors from Rn. We've talked about when two vectors are orthogonal, right? What is the condition for two vectors from Rn to be orthogonal to each other? Yeah. Yes. The standard product is 0. This is also equal to. Yeah, that we know. And what is the standard inner product? What will it work out to? I throw of what? Okay. I throw. How many rows does X have? N. N rows. You're right. Okay. I throw of. Hey, hold on. How many columns does it have? See, this is already what you're saying. This is a 1 cross n matrix. This is a n cross 1 matrix. The product is simply the inner product of the first row and the first column. I'm asking what will this work out to in terms of the components of x and y. What is x? x1, x2, xn. Similarly, yn, no? y1, y2, yn. What's x transpose y? This you have to know by now. Sorry? What is the expression? Just tell me the expression. It doesn't matter. I, k, y, a, j. 1, 2, n. Okay. Right. Here. But it's not I. There is only one row, one column here. So this is just 1, 1, or it's just xk, yk, no? You multiply the individual terms and add them together. Okay. So this is clear. Okay. Now, if you have a set of vectors, okay, instead of just one, two vectors like this, let's say you have a set of vectors S, x1, x2, xp, and each x belongs to Rn. If you have a set of vectors, we say that this is an orthogonal set of vectors. Vectors, if you take any xi and take its inner product with respect to some other vector, not the same vector, some other vector, then you get 0. Then you say that this is an orthogonal set. That means every vector here is perpendicular to every other vector. What will happen if you do xi transpose? Well, it need not be 1. Well, can it be 0? No, it can never be 0. Right? So my question is, can it ever be 0? X transpose X, can it be 0? No? Right. So X square can never be 0. X is a real number. Yes. So what is the condition for this to be 0? Yeah, if only if it's a 0 vector. 0 vector, this will be 0. Otherwise, this is always greater than or equal to 0. Okay. So if you have this condition that's satisfied, then you say it's an orthogonal set of vectors. But in addition to this, if xi transpose xi is 1, then the vectors are all orthogonal to each other and they are also of length 1. Then it's not just orthogonal, it's orthonormal. Orthonormal set of vectors. Okay. That is when xii transpose is 1, xi transpose xj is 0, where I is not equal to j. Okay. Now, if I have a set of vectors S that is orthonormal, okay, is that set linearly independent? What do you think? It is. Why? Why is it linearly independent? Hey, hold on. Okay. For something to be basis vector, it has to be linearly independent. You cannot say it's linearly independent because it's basis. Because I'll ask you, how do you know it's a basis vector? It forms a basis for something. Sure, but how do we? Okay, yeah. So you simply go back to the definition of what linear independence is. What is the definition of linear independence? There are these p vectors. That means if I take the linear combination of these p vectors, alpha p plus p, and this is equal to 0. Under what condition? If this is satisfied only when alpha 1 equals alpha 2, alpha p equals 0, then we say it's linearly independent. Any other non-zero values for alpha 1 to alpha p that gives me this is linearly dependent. And the reason that this is linearly independent is, if let's say we have this expression, we are interested in finding out, are there non-zero alphas that give me this? You simply take the inner product of the left hand side with x1. Okay, 0 multiplied by vector x1 is 0, so right hand side remains the same. So if you take the inner product, then you that means I take this whole thing and I multiply it by x1 transpose. Okay, for inner product, the scalar can come out. That means if I write this down, this will be simply alpha 1 x1 transpose x1 plus alpha 2 x1 transpose x2, so on and so forth, to alpha p x1 transpose xp, and this will still be equal to 0. Because the right hand side, if I multiply the row vector by 0, I get 0. Now, what happens here? We know from here, the first term is 1. This is equal to 1, right? That means this becomes alpha 1. What about the other terms? They're all 0 because by definition, they are perpendicular to each other. That means what I'm left with is alpha 1 is 0. This is the only way I can get the left-hand side to be 0. Now, that means for this expression to be true, alpha 1 has to be 0. Now, if you take the inner product with x2, you'll see alpha 2 is 0. That means all alpha 1 to alpha p have to be 0 for this expression to be true, which means it's linearly independent. Okay, that's simple enough. Because it's linearly independent, if you take the span of S, okay, this set S will be a orthonormal basis for the span of S. I hope that's clear. See, the span of this will be a subspace. And because this set is a linearly independent set, that means it's a basis for its span. And because it's orthonormals, it's an orthonormal set, it's an orthonormal basis as well. Okay. All right. Now, it turns out this idea of orthogonality can be extended not just to a set of vectors like this. In fact, even bigger structures such as subspaces. Okay. Let's say we have two subspaces V and W that are subspaces of Rn. Let's say proper subspaces. What does it mean when I say V is a subspace of Rn? What do I mean? Vector space, right? V is a subset of Rn and it's a vector space. Similarly, W. Okay. It turns out you can talk about orthogonal subspaces. Okay. And the idea is simply this. You say two subspaces are orthogonal to each other if you take a vector V from the vector space, the subspace capital V, and you take a vector W that is from the subspace W, and you take their inner product, and you get 0. And this is 0 no matter what element you choose from V and no matter what element you choose from W. Then you say that, and their standard inner product computes to 0. Then you say the subspace W is orthogonal to subspace V. Okay? Or you would usually write V perpendicular to W. Okay, all right. With that, okay, let's say we take R2. Okay, okay. This line, that's the subspace of R2. And what does an element from this line look like? What will be the expression for an element from this line that passes through the origin? Alpha 0, right? The second element is always 0. I choose 1 from here. This is a subspace. Let me call this V. This is a subspace. I call it W. What will an element from here? 0 beta. Are these two orthogonal subspaces? Well, a general element from V looks like this. A general element from W looks like this. If I take the inner product, alpha 0, V transpose, 0 beta, 0 plus 0, I get 0. That means this is 0. No matter what element I choose from V and what element I choose from W, those vectors are orthogonal to each other. That means the subspace V is orthogonal to the subspace W. Okay. What about this subspace? Let's say I'll call it V1. This is of alpha alpha. This is a subspace W1. The element here is beta minus beta. Are the W1, so from this we know V is orthogonal to W. I want to know if V1 is orthogonal to W1. Yes. It is orthogonal. So if you take any element alpha alpha, inner product with beta minus beta, alpha beta minus alpha beta, this is 0. That means any element that you take from this is always orthogonal to any element from this subspace. Okay? We'll simply finish off the with a set of examples from R3 and then we're done for today. What about R3? This is a subspace of R3. This is origin. This is a subspace. For now, we'll call it the x-axis. Okay. The y-axis is a subspace. Are they orthogonal subspaces? They are. What about x and z? What about y and z? They are. Okay, all right. What about the xy plane? Is that a subspace of R3? XY plane. That's this plane. Z is coming out. XY plane is a subspace. We know the Z is a subspace. Is the XY subspace orthogonal to the Z subspace? Okay, all right. What about the XY subspace and the XZ subspace? So that means this plane and this plane. Are they orthogonal? Are all vectors from both these subspaces orthogonal to each other? So XY and XZ. Okay, what does the XY subspace look like? Alpha, beta, 0, right? This. What about the XZ subspace look like? Well, gamma, 0. Yeah. If you take the inner product, this is alpha gamma equal. Well, that's it, alpha gamma. Is this always 0? No, depend. Here, what if I choose 1, 0, 0? That is from the XY subspace. I choose 5, 0, 0. This is from the XZ subspace. The inner product is not 0. That means the XY and XZ are not. That's because their intersection is the x-axis. Okay, that's why it's not. So in 2D, in R3, you have a plane. So two-dimensional subspace. You can only have a single one-dimensional subspace that can be orthogonal. You cannot have two-dimensional subspaces in R3 that are orthogonal to each other. Okay, all right. With that, I'll stop and then we continue this tomorrow.